All right, so in this section, I just wanted to stop and take a look at how we can do a little bit of, just some workflow stuff by creating an automated, Rubble kit bash generator thing for us. So we can write out OBJ files to disk and use Houdini in a way to just sort of automate and create things for us. So let's I've got a new scene here. I've saved it in my project structure I normally do, but under just want to make sure that under aliases and variables, I've got my $hip variable is pointing to my project structure. So it is. I'll be using that later when I'm writing files out. So to create this Rubble generator, let's just throw down a geo, and I'm just going to name this Rubble generator. Cool. So now let's jump inside here, and I'm going to generate some concrete chunks. And to do that, I'm going to just shatter apart a box. So let's throw it on a box first. I'm going to add a box here, and then I'm going to use a new node, which is called RBD Material Fracture. And RBD Material Fracture similarly is a new asset. You can see it's got to think a little bit when you first throw it down, but once I wire this box in, you can see that by default what it does is it kind of does a Voronoi style fracture. I'm just going to throw down an exploded view. I like to keep one of these handy when I'm doing any sort of fracturing stuff, and I'm just going to break it apart so I can kind of get a view of what the inside is looking like. And it's looking pretty plain right now, but if you look in this RBD material fracture node, it's actually got quite a few options for us. If you even dive inside, you can see it's a digital asset with just a ton of functionality built in. We don't really need to worry about what's going on inside of it, but just another example of all the beautiful setups that the side effects team has made for us. So I'm going to just get up here and under concrete, we can select different material types. We could do a glass style fracture. So if you had sort of a thin surface, something flat, it would kind of start to create sort of a glass fracturing effect. It doesn't really work on a box that is this size, but if I were to, kind of scale the size in Y down a little bit to maybe so it's only a tenth of the height, you can see how this shatter's starting to look a little bit more like glass. You can modify some of these settings, talking about how many radial crack points you've got, variances, concentric cracks. You can change all that stuff. I kind of did too many, so I'm hitting escape so I can stop it from cooking because I don't want to crash my computer. But then you can work on creating little chips. So a little secondary crackling to it and all sorts of features to explore with this. We could do maybe some more. Yeah, if we create detail, we decrease the size of the detail to something a little bit smaller. You could probably add a little bit of more interest into your fractures. So there's the glass option. There's also a wood option. The wood option will bring up a whole different set of stuff here, but if I were to make my box a little bit longer, like make it, I'm going to make it about 10 in the X value, you can see that it's doing a fracture that looks like wood splinters here, and it's using a different model. But here what we do is we get grain. So you can see before I do the exploded view, you can see we get these vertical lines that are kind of wavy where it's inserted like what would be like wood grain, so that these fractures sort of resemble like the warping of the grain inside of a piece of wood. You can change the spacing of that, and you can increase it. And you could also, I could change the element size of the grain noise. You can see how it's wiggling a little bit. These vertical lines are wiggling a little bit. If I made that element size a little bit larger, it would wiggle with a lower frequency, but I could increase the height to something a little bit more visible to us. You can now get some bigger waves in our grain. There's clustering. So if I were to break apart this, again, using our exploded view, and if I turn off clustering, you can see there's all this extra geo. Disabling enable cluster, you can see this is how many pieces that it's generated. Well, to create sort of a more realistic and random look to it, because this is very uniform, and wood generally tends to want to hold itself back together, we could enable the clustering, and it will try to grab grab pieces and put them back together. Enabling random detach will kind of break some of them back apart, and you can set a ratio as to how many of those are actually coming back apart in the end. So those are all fun things to check out. For our example, I'm going to just reset our box back to I'm going to set it back to a 1x1 box. And we're just going to create some concrete chunks. But you could easily do this for any type of geometry. It doesn't even have to be, fractured geometry. You just, eventually you're going to get to the point where you're making all sorts of procedural stuff, and you might want to kick that out into another program. So here, I'm going to switch back to concrete fracture. Which is, at this point, very simple, like our Voronoi fracture. And I'm just going to switch over to the detail section. And here I can add interior detail. Interior detail just adds a little bit of noise to the inside with a fall off from the edge. So if I were to maybe increase the noise of the interior detail, you can see it gets very gnarled up. But if I were to just kind of zoom in on this edge right here, you can see we've got a flat edge, and so we need to blend between this flat edge and all this gnarly noise in the middle. That's what this option does, this depth, volume, voxel size. If we increase that, you can see that the noise is only starting to occur as we get closer to the center of our geo. So there's an option for adding detail. I like to do the edge detail option, and this totally does a different type of fracture. It uses more of a Boolean fracture, but now our edges get this nice kind of wavy lines to it. It looks starting to look more like concrete. So I'm going to just maybe increase the height of the noise to something a little bit more aggressive. So I put in a 0.3 there. And you could also adjust the noise element size. You can make it bigger or smaller. I think in my case, I'm just going to try maybe 0.05. That's way too much, way too high frequency of a noise. Let's see, where were we? Maybe, was it at 0.2 originally? It looks like that's the default. Just a quick tip here. You notice on our settings here, if you ever have you want to reset to a default, you can right click here and then say revert to defaults. If you're not on a default, notice how we've changed the noise height. This is like a more bold number now. This is a brighter 3.3 than this 0.2. When it's brighter like that, that means that it's been changed. And likewise over here, because we've changed something on the detail tab, it has been bolded. So you can actually kind of track where things have deviated from the default by following these bolded numbers. So just a quick tip there. But so this is looking pretty cool for our concrete pieces for right now. I mean, you could mess around with this all day to get a result that you like, but for our purposes, let's just move along and start working on how we can get this out into our directory on our disk that we can load into another program or just load back into Houdini in general. So I'm going to, let's see here. I think what we're going to do at this point is it's time for a for each loop. So let's throw down a for each. Oh, and before I do that, I'm going to just make a note real quick here. If I select my info view, you can see that the RBD material fractures actually created a name attribute for us under our primitive attributes. And that name attribute is something that is generally created by objects that are doing fracturing or Voronoi or anything like that. The name attribute is basically a unique identifier for each primitive to tell it which piece it's a part of. So, we've got all these individual polygons, but this name will help it determine that it's actually a part of this whole chunk. So this polygon right here knows that it belongs to this whole chunk because RBD material fracture was smart enough for us to create this name attribute. And because we have this name attribute, we can use a special preset of the for each loop to iterate over those names. So instead of iterating over every single primitive in our group, we can iterate over individual chunks. So let's do that. Hit the tab key, start typing for each, and you can see we've got over here, our second option is for each named primitive. If I click that, you can see that by default, if I go to the for each end, it is looking for primitive piece elements, and that piece attribute is name, which exists up here. So if we wire this in, and I just select oops, I have this selected on the wrong input. Wrong input here. If I just move this over to the leftmost input on our RBD material fracture and go down to the end here, it's storing an error. What is it saying? Invalid attribute specification name. It doesn't make any sense because RBD material fracture is supposed to be creating a name for us. Let's try and debug this a little bit. It's looking for a name piece attribute. We've got a name piece attribute right here. I mean, this should be working. I'm not quite sure. If I scroll to the end here, yeah, I'm not getting anything. Switch to single pass. Okay. Well, it looks like it's working. No, it's still not working. What's going on there? Okay. Now it's going through. Okay. Yeah, let's click this single pass again. Okay. Something weird was going on there. I just needed to kind of uncheck a few boxes and jostle something loose. I'm not sure what quite happened there, but certainly we had a name attribute. It was coming through, being picked up, and it just needed to be reassured. Sometimes if you just move your display flag around to a bunch of different nodes, it'll all sort of sort itself out. If not, certainly you could try deleting these nodes and throwing down a new for each named piece preset. So cool. Now what I want to do is, now that I've got this for each, I want to just bring every single piece back to the origin. So we're going to use the centroid function as we have in our previous lessons with at various points. I'm just going to put a transform inside of our for each. So let's throw it on a transform. And I'm just going to wire that in right here. And now I have only single pass checked. That just allows me to look at each individual rock as a single pass in our loop. So I'm just working on single pass 0. And I'm going to just, in the translate section, I'm going to just enter in a little expression here. I'm going to type in centroid. And I'm looking for the centroid of the first input of this. So that is, because computers start counting from 0, that's going to be the centroid of the 0th input. And I'm going to want to look at the d_x dimension. So just d_x, and that is going to translate it by the offset of x. But we want to move it in the negative direction since we're bringing it back to 0. So if I put a minus sign, if I put a minus sign in front of the centroid like that, it moves it back to center. I just need to copy this expression to each of my other fields here. So if your value is evaluating to a number now, you just click the translate. It re-reveals the expression. Just going to copy it, hit tab, hit paste, and change this to y because we're in the y field. And I'm going to hit tab again and hit paste and change this to z. So now it's centering our geo on the origin in all 3 dimensions. So now when I scrub through the single pass, you can see everything has sort of been centered. And if I untick single pass, you can see all of these chunks are centered in the center of our scene. So now what we can do is, let's just kick all these out. We don't really want to kick them all out like this though. They're all overlapping one another. Well, what we can do is we can actually use the frame of what we can tell the single pass to only evaluate which frame we're on, which is kind of cool. So if I type in at frame, like so, now this is actually going to evaluate to whatever frame we're on. So now when I scrub my timeline, you can see that it will evaluate to whatever piece we have. Cool. And so we could actually use this with our file caching abilities to create a directory full of individual pieces like this. So let's do that. I'm just going to throw it on a file cache. Now there's a number of ways that you can, not a file, but an actual file cache. There are a number of ways that you can get geometry out of Houdini. If you're working in Indy or above, you could also use your Alembic, the ROP Alembic output, which is a similar node right here. It gives you options for what frame range you want to use, where your output file you want it to be written to. So that is another option for exporting geometry. Not available if you're on Apprentice, I believe, but just to know that it's there. Also, there's the ROP output driver. or ROP geometry output. This is another node that you can wire in and gives you also, a frame range, your file name, and you can write files out using this as well. I like using the file cache just because I'm used to it. It loads geometry back for you when you're done with it. If you actually dive inside, it is a digital asset that has its own ROP geometry output node buried inside of it, which we don't even have to think about setting up because it's kind of done it for us here. I just really like using this node. So I'm going to wire in the end of our for each loop here, and it looks like we had what, 24 frames worth of pieces. What I do know is that these for each loops begin because computers start counting at 0. There is a pass that we're not actually getting access to because we're evaluating to frame 1 when there actually is a pass number 0. So instead of frame, I'm just going to hit frame -1 so that we start counting from 0. And if we go from 0 now to 25, we get all of our pieces in this group. So just a little thing to keep an eye on is, if you start counting from 1, you might actually have a 0 pass there. So subtracting 1 from it, simple enough. Cool. So now here we're going to be writing out files by default from start, our start, end, and increment. We're going to be writing out to frame 240 by default. If I click this, that's $FN, which is evaluating to 240. That's our frame range. I can just right click on this and say delete channels, and then I can change this to 25 manually. And it will, write out our pieces for us. Alternatively, what I could do is I could count up the number of pieces up here and, reference create some expression to reference how many pieces we have. So I'm just going to do that real quick. I'm going to actually, because creating like a counter, an automated counter for us, if we wanted to change the number of pieces, this value would change. And it wouldn't dynamically update. We'd have to go update it by hand, but there's a better way. We could throw down an assemble, for example. And if I'm not going to wire this into the main geometry, because if I do that, it tends to make it so that things don't work. Because what I want to do is, if I middle mouse click here, you see I have tens of thousands of primitives, but I really only want the 25 unique named primitives. So if I go here, I don't need to create a new name attribute. I just want to create packed geometry. Packed geometry now is recognized as I mouse over. Each individual piece now is like an entire chunk. By comparison, before on our exploded view, if I were to mouse over, select this exploded view. If I were to mouse over, you can see I'm highlighting each one of these individual polygons as I slide over it. If I wire the exploded view into the assemble, now every time I mouse over, it is recognizing an entire piece. And if I middle mouse click on here, you can see that there are 25 primitives, endpoints, and vertices, etc. This is what packed geometry is it basically creates a memory efficient representation of the geometry by packing pieces together in a relevant way. It's a little bit more complicated of a concept than what we really need to know at this point for our lesson, but it's just important to know that it's there and we can use it. So, because using this now is going to break our for each loop, I don't actually want to have this be in line with our network. So I'm going to just shake it off, and then which disconnects it, and then I'm just going to wire it back in. So over here, we've got our assemble where all the pieces are assembled. And then down here, we've got our individual chunks and we scrub through and we've got all of those. So if I was down here, I could write an expression that references up here and determines, I don't need these, I'm going to delete them, references up here how many individual loops it should make. So let's go and I'm just going to create a null to make it easier to find. I'm going to wire the assemble into the null and I'm going to say, count me. So all we got to do is tell our file cache's end frame to look at count me and determine how many primitives are in count me. Because if I middle mouse here, you can see there are 25 primitives. So simple little expression is simply n prims, all lowercase, n prims, and open parentheses, And then I'm just going to start typing the path to count me. So open quote dot slash, and you can see our first option is count me. I'm going to hit the down arrow. Whoops. Dot slash count me. I'm going to hit the down arrow and hit enter, and then close parentheses close quotes and close parentheses and hit enter. And now we've got this function in here. And if I click over here, you can see it's evaluating to 25. So now a cool thing is when we go to write out our files, suppose you want to actually change the number of fracture pieces you have. I could change my initial fracture points to something like maybe 15. And it's going to think about it, and it's going to generate a whole bunch more pieces for us, like so. And you can see from the exploded view, we now have more pieces. So it's going to go through this for each loop, and it's going to go off to this assemble. The assemble is going to evaluate now that we have 75 pieces, and the file cache down here also sees, because we entered in that expression, that it should go from frame 1 to 75 and write out the files as such. So with that all being done, I'm just going to make sure they're going into the right directory. So $hip, which we made sure was set in our edit aliases and variables, our hip file. So this is going to be the initial path that it goes to our project file. It's going to write a file next to our project file called geo. Cool. And then it's going to write out this string, which basically is the file name and the operator name down here, and $f.bgo.sc. $f is for which frame we're on when it writes it out. I'm going to just kind of modify this to do my own thing. I want a folder named after this. So these are concrete pieces, like that. I want a folder after geo that's called concrete pieces. So like we have up here $os, I can just create a folder called $os / and then I'm just going to name these by hand. I'm going to just call this concrete piece, and then it's going to say concrete piece dot whatever frame we're on. So, it'll go 1 through 25. That's good. And then .bgo.sc. In our case, a nice portable file format we want to use is .obj. So it's as simple as just changing this extension from .bgo.sc to .obj, and you're good to go. So if we go down here and click on this, and then I'm just going to hit save to disk, and we'll get a little progress bar that pops up. It looks like it's rendered all of it already to memory, but it's still writing files to the disk. So I'm just gonna pull up my Explorer. If I go to, let's go here, lesson files, lesson 3, F, and then so it's created a geo folder, and in here it's created a concrete pieces folder for us. It's got this wood pieces in here because I was working on a previous example, but our concrete pieces folder has been created, and here are all of our concrete OBJ files that we just made. So that is a cool way that you can use Houdini to automatically generate geometry for you. And this is a really simple example, but you could do this with all sorts of stuff. If you were creating procedural buildings and you had variations that you wanted to kick out, for example, if you were adding randomness every single frame to, a terrain object or something like that, you could use this to automatically create all sorts of stuff for you. Just another little quick overview of how the file caching system can be used in tricky ways, along with for each loops, to kind of create some really great automated workflows. So in the next lesson, we're just going to go over a little bit of a formality issue with for each loops versus copy stamps, which you would find in older tutorials. And then we're going to get into attributes. So without further ado, we're going to end the lesson and then move into the next lesson, and I'll catch you over there.